All right. Okay, welcome to our September VAST, first of the new academic year. It is also the start of our fourth year of doing VAST. As such, the organizers have really expended a lot of our links to finding software projects in our circles. And so we are looking for people to join us as organizers. And if you are interested to join as an organizer, we figure it's about 2 hours of work a month or so, including the session that we're in right now. You can sign up and hopefully someone will share the little Google form that we had created on our chat and you can join us. To kick things off, since we're usually sitting in the background and listening to others talk about their fantastic software projects, we thought for the start of year 4, we would tell you about some of this work that we do in the software space. And so we'll hear from 3 of us today about that. 2 other things. We are looking for talks about organizing communities, and we already have something lined up for next month about that. And we are also looking for people who have used AI, not as a tool for the data analysis, but have used things like Claude or the various coding tools to help them with their workflows. So writing code, reviewing code, writing test cases, such like that. So if you've had experience, good or bad, about using AI tools to help you with your coding workflow, that's something that we would like to talk about in a future session. And you can post an issue saying that you'd be interested in talking to that, and we'll get that issue link also dropped in our chat in just a bit. So we're going to hear from our very own Alice Allen of the astronomical, oh geez, now I can't, software,
Astrophysics.
astrophysics. She'll tell us what ASCL means. I love the coffee
Yes.
so far.
All right.
So we'll hear from Alice, starting out about ASCL, and then myself, and then our very own San Dunham to wrap things up, and we'll have some open discussion afterwards.
Okay, so we'll see how this goes. I am hoping that you are now looking at my slides.
Yep.
Yes, okay. Thank you very much. Thank you, Michael. So this is a project that I'm really, really excited about. I'm so excited about it. I've been working on it for 15 years for free. So that tells you it's kind of cool and I really like it. So my name is Alice Allen. I'm the editor of the Astrophysics source code library. And I'm going to show you some tips and tricks, but I probably first should do a little bit of introduction into what the ASCL is. So the ASCL is a registry of software used in refereed research. We have a pretty broad definition of refereed, so don't worry about that. It used to be a repository, but when I started working on it 15 years ago, we dropped the need for people to store their code in the ASCL and now mostly point to where the software is, such as on GitHub or GitLab or institutional websites or whatever. But we can still serve as a repository and if you're leaving the field or something like that, we want your software because we want to make sure that it continues to be around to support the science that was done with it. And the ASCL is indexed by the ADS, which is the Astronomy Data Service that's run out of Harvard CFA. It's also indexed by Web of Science and other indexers, which means that they ingest our information. And the reason that we do this is because we want to increase the transparency of science. So we register codes. There are 2 criteria for a code being in the ASCL. The first is that it's used in refereed articles. But for refereed articles, we also mean articles submitted for refereeing because astronomy has a very high acceptance rate. And we also include accepted PhD theses. We consider those refereed as well because they've had to go through a committee and all. The other criterion, so there are 2, used in refereed research, and the other one is source code has to be available for download without barriers. If you're reading a research paper and you come across a computational method, you should be able to look at that computational method. There should not be black boxes in science. We want to increase the transparency. And one way to do that is to make the software more easily found, more discoverable. So that's why we do this project. So we often create entries ourselves, but we like it when people register their own software because the software authors know more about their software and generally can write better descriptions. I frankly hate writing descriptions for software, especially when there's very little information on a GitHub repo or in a paper about the software. So please help me out and write the descriptions. Even if you just put it in your README, that is a help if I'm coming along and finding your code somewhere. And want to add it. So what do you get out of registering your ASCL ID? You also get entries for this software in ADS, Web of Science, Google Scholar, etc. So there are more places for people to learn about your software. You get a trackable citation method. There are numerous ways to cite software. Some of them are very bad, and some of them are very good. The ASCL ID can be used to track citations, and that I consider a good method because it's trackable. So you can use an ASCL ID to cite the software, and then ADS and other indexers pick up those citations. If you try to cite a software package by just a GitHub URL, for example, that's not a trackable method. So one of the things we wanted to do was to provide a trackable method. And once we did that, a lot of other people also started providing trackable methods. And that's really good for the field. I don't care how you cite software as long as it's a good method. It doesn't have to be by ASCL ID, but it could be. You could also use a Zenodo DOI and other ways. And this increases the discoverability. As I said, the whole reason we do this is because we want to improve the science and make it more transparent. So let's, okay, so you can retrieve a code quickly. I'd like to switch to the ASCL to try this out. So let's see if I can do that. I have to stop sharing first, I think. And share again. So sorry for this. I want to share the ASCL. I hope you're looking at the ASCL, yes?
Looks good.
Okay, thank you very much. So this is the homepage of the ASCL. You see that there are options up here. The 10 most recently added codes are on the home page. So you can retrieve a code. So you can search for a code up here. We have a full text search box, and you can search for a code, for an author, etc. up here. But if you already know the name of a code, for example, let's say you know the code apple pie, you can simply append the, if you can type, you can append what we refer to as the alias or the name of the code right to the ASCL URL. So if you add that there, you can bring up a code just by using what's called the short name or the alias. This is typically the information that appears before the colon in a title. So that's really good if you already know what code you're looking for. So that's one tip. A lot of people who are always looking at codes and know the names of the codes and want, for some reason, maybe to look up the preferred citation method in ASCL or other information in ASCL. That's really handy. The data editors at AAS journals were very happy when I showed that they could do that because they did not know. You can also, of course, use the search box to find things. Another thing that you might not know about the ASCL is that you can grab all of our data. All of our public data is available through a link. So if I add code /JSON to the URL for the ASCL, I get all of the data. So there's all the raw data. I can make it look prettier with a pretty print. but it's all there in JSON. So if you want to play around with the ASCL data, you are welcome to do that. I don't know why you would want to do that, but people do that, and then they show me really cool applications that they've done, different things that they've tried with that. You can see all of the citations that ADS has tracked for a particular software package, for Apple Pie, for example, by clicking the bib code in the ASCL entry. So if we click this, this is the ADS record, the Astrophysics Data System record. Because they ingest us, they have the record here. You can see that this code, the ASCL entry, has been cited 738 times. So that shows that citations are accruing to this code, to this software package. You can also see over here that there are related materials. We list papers that describe or use a URL in our entries, and ADS picks those up. We don't list all of them because we would want you to use citations for that. But this is a good way of relating software that's been used in papers with those papers, and also papers that use software with the software. Because if we click on this, there's a related materials over here for the source software. So if you're looking at a paper, you can click over here, get the ASCL ID, go to the publisher, look up the entry, and then go look at the code. So within a couple of clicks, you get to look at that. You can search, let's go back to ADS, because this is something a lot of people don't realize. There are different document types in ADS. I'm sure you're familiar with published articles and preprints, conference proceedings, but there's also a doc type software. So if you type doc type software, you can see all the software packages that ADS has listed. So that's another way of, so these are generally things that have been cited at least once in refereed research. So there are lots of records out there, a lot of Zenodo records, a lot of ASCL records. So that's also available to you. You can, once you've found software, if you want to use a keyword, for example, let's say you're interested in NASA software, you can add a keyword to that as well. So that limits your results to a smaller set that maybe have what you want. So let me go back to, let's see, did I show you? I showed you all of that. So let's go back to, I'm so confused here. All right. Too many screens, and one of them slid off the desk for a little bit ago. So let me go back to the presentation. So are you now seeing the presentation again?
Yes.
Okay, good. Okay, so you can retrieve a code quickly using its alias. You can download all of our public data. You can see citations to ASCL entries. You can check out related materials listed on ADS. You can search ADS for just for code, and you can search ADS for code using keywords as well. So there's a lot more information. There's an 1.5 hour long video tutorial that's available. And these slides will also be available both on the ASCL and on, I presume, the VAST. We'll link them somewhere, but they'll definitely be on the ASCL in the news area on ASCL. You can read more about the ASCL at ASCL/about and its policies. You can check out an interactive poster that gives you even more tips and tricks. You can email me for questions. So thank you very much. I think that's my time. Thanks.
Thank you, Alice. We had a couple questions in the chat. Do we want to address those real quick before we move on, or should we?
It's up to you.
Yeah. Yeah. So both these I think are from Michael. The first one says, what about code that is described in in a journal like the research notes of the American Astronomical Society? Those aren't technically refereed. Are they still ASCL-able?
No, it has to be used in refereed research. And that's the same issue with JOS. JOS is a paper, but it's typically not research. It's not a research paper. So JOS and research notes of the AAS do not count, but a lot of times something is, if it goes to JOS and or to the research notes, there typically will be a paper following at some point. So we encourage people to still go ahead and register their software with the ASCL, and then when a refereed paper or when a preprint is submitted for refereeing, let us know, and then we'll assign the ASCL ID at that time. So people, if you look at the ASCL, you'll see that there are lots of entries that say submitted, and it's just because we're waiting for some essential piece to come, and it's almost always a paper. And the reason we do that, we could list a lot more software if we just took all astro-software. But the reason we don't do that is because we're trying to improve the transparency of research. We're very research focused. And as I said, if you're reading a paper, you should be able to see it. People do write software that never gets used anywhere, and adding that to the ASCL would increase the noise in ASCL. That's not what it's for. I think it's really good that there used to be a project that would do that had extensive software that was not in ASCL, and I thought that was really great. And it disappeared one day. So I'm sorry about that, but that's not what the ASCL is. So it's very research focused. So let's see.
Great. And then as a quick follow-up, Michael asks, he says the ASCL entry for a code typically includes the authors from the first code paper.
Right.
Is there a way to update authors as more developers join the project?
So we don't want to mess with an existing entry for the ASCL, but if the software has been updated a lot, and in part because you've got new people working on it, we would like to, and it gets used in research, we will create a new entry for it with the updated version and the updated author list. So the problem of mutable author lists is very difficult to solve. And, you know, it's something we kind of key off of what ADS does and does not do, because we want ADS to index us, because that makes software more discoverable across the board. You don't have to know about the ASCL to still find ASCL entries if you're going to ADS. So we key off of them. I know that they're trying very hard to find ways to solve that. Zenodo has the many versions thing, where every time you add somebody or make a version change in Zenodo, you can push a new Zenodo record to ADS. And that's really good for transparency, but it's making it hard on ADS because they sometimes end up with 40 records for one software package. And that is not helpful if you're trying to track total citations to realize the impact of that particular software on research, because then the citations are spread across a lot of different versions and it's hard to roll them all up. So that's nothing, it's not perfect, but we do what we can. So we will do another entry. Good questions, Michael. Thank you.
Thanks, Alex.
Great. Well, I think that was all for questions in the chat. Shall we move on?
Yes.
Yes. Yeah. Michael, were you going to go next? Yes.
Yes.
Great. Okay, so next we have Michael presenting on Pynucastro, a Python library for nuclear astrophysics. Take it away.
Oh, look at that. Look how many Jupiters I must have open for the port to be that high now. All right, let's see. You can see my screen?
Yes.
Cool. All right, yeah, I'm going to talk about Pynucastro, which is a library that started, I think about 10 years ago or 12 years ago, when I first taught the graduate class on stars at our school. And we had trouble with some homework of integrating reaction networks. And so this library was born out of that. So I'm going to do it all via Jupyter. I'm just going to give a quick tour, and I'll drop a URL in the chat after I go through this. So Pynucastro is basically a library that allows us to interact with data from nuclear experiment that has knows about reaction rates. So this can come from a variety of different sources, and we do our best to provide a simple interface to interact with all that nuclear data and then explore it and ultimately build a reaction network that can be used for simulation code and export that in Python or C++, and we have Fortran wrappers as well for that. Traditionally, let me make this a little bigger. Traditionally, we import it and we rename it as PYNA just to save on typing. So, for instance, we can look at a nucleus, and so here's the nucleus nickel 56. We just say nickel 56. You can make it caps, you can make it lowercase, and I can ask for a summary, and this is everything we know about nickel 56. It's atomic weight, number of neutrons, number of protons, its mass excess, which is usually what is tabulated in nuclear experiments, binding energy per nucleon, which is what we usually care about when we're thinking about the energy that comes out of reactions, half-life, whether there's a partition function that's available for it, whether there's what the ground state spin is, and these are things that are used for some bookkeeping. One thing that you need when you're working at very high temperatures is you need temperature-dependent partition functions, especially when you're doing nuclear statistical equilibrium and you're doing detailed balance to get reverse rates, and we can access them. We get them from compilations from Tommy Roscher, and so I could say, give me the partition function evaluated at 5 × 10⁹, and it's a little bit more than 1. Otherwise, at cooler temperatures, it's just 1. There's a popular library called ReactLib that has about 80,000 reaction rates, mostly for strong interactions, and it gives us the temperature dependence in a very specific format. And we can read them all in, and I could say read in all of ReactLib, and this creates a Pynucastro library that knows about all those rates. And then I can say, I want the rate of carbon-13 plus a proton, releasing a gamma, making nitrogen-14. This is how we would write it in a paper, for instance, and I can use that same notation to query the rate, and it'll get me that rate. And so it prints it out in a nice, pretty way, but I can also evaluate it. I can evaluate its temperature dependence, pass in a temperature in Kelvin, and it tells me this is what the rate is in units that we won't. It's all CGS because we're strong. Sometimes we want to know just how temperature sensitive reactions are around some point, and so I could say, give me the power law exponent for this rate about some temperature T0. So for instance, about a temperature of 20 million Kelvin, and it tells me that this rate, which is one of the limiting rates for the CNO cycle, it goes like temperature to the 16th power. So you increase temperature a little bit, the energy generation will go up as that amount to that ratio to the 16th power. And we could plot it, and we can manipulate the plot, and this shows that over this range of temperatures of about a factor of 10, the rate increases by 8 orders of magnitude. If you go to ReactLib and you get the reaction rate itself, and you can download it, you can download the whole library, you can just get a rate, you'll get something that looks like this for the rate. These are These are 3 sets that describe the same rate. This is sort of the base, and these are resonances for the rate. And each one has 7 numbers, which are coefficients to some very complex exponential fit with temperatures to fractional powers. And so this is what you would have to deal with if you want to work on the rate itself, but we know how to deal with this natively. And in fact, if you want to generate Python to compute that rate for you, we can just get a function string in Python, and this is Python code that will compute that reaction rate. Of course, the library will compute it internally interactively, but if you want to export the rate to your own Python module, you can output that. You can also output C++ code for it. It's a little bit longer because we do some templating to speed some things up, but it'll compute the same rate. And we actually directly compare the results we get from Python and C++ to make sure they agree to floating point precision. If you want to build a network, there's lots of ways you can do this. One is you can say, here's the list of nuclei I'm interested in. So proton, deuterium, helium-3, helium-4 for the proton-proton chain, and then nuclei for CNO and for hot CNO. And you give that list and say, from ReactLib, find all the rates that link those nuclei, and it does it. And I can actually just see what those rates are if I just look at the library, and it found all these rates, linking them. Some are reverse rates that are very endothermic. We'll talk about those in a second. And I can generate a network given a library. You can pass in a bunch of libraries that use different sources. And a network is basically that collection of rates and the knowledge of how to actually evolve that set of rates to find what the energy generation rate is. This is a Python network. It's a specialized network that can output Python code. There's various C++ networks, one which outputs code that runs on GPUs for our simulation code. And there's a Fortran network that just wraps one of the C++ ones that was created in response to a user request. I can plot the network, and this shows me an overview. This is proton number, this is neutron number of all the nuclei and all the rates that link them together. And so you can see there's a lot of connections here, even for just this small number of nuclei. I can ask for a summary of the network as well. And it tells me it's carrying 11 nuclei. There's 26 rates. They're all ReactLib rates. We have other types of rates that we can do. We can approximate rates, so combine multiple rates together into an effective rate. We can use tabulated weak rates. We can rederive reverse rates. We can modify rates to say, I want to use that rate, but I want to change its endpoint or change the stoichiometry to it. Or we can just create our own rates, and it'll keep track of all those. I could create a thermodynamic state. So conditions in the center of the sun, density of 150, temperature of 15 million Kelvin. I'll create a composition of just those nuclei and make it something like solar. And I can evaluate the rates. And this tells me what the rate is, including the density and composition terms for our network for each of the values. A lot of these are 0, so they can probably be ignored. Some of them are reasonably high, like the proton-proton ones, or this one. We can also plot and show how strong the rates are in our plot, and we can make the edges. We use network X for this. We can make the edges curved to show the difference between the forward and reverse rates. And so we can see some of these rates are just not important at all, including the triple alpha. Where's triple alpha? Well, triple alpha is like somewhere around here. But the proton-proton rates and the forward rates in the CNO really seem to be important. One of the challenges always when you're doing simulations and multidimensional simulations is you want to pick a reaction network that is large enough to give you the right energy and give you a good estimate of what the nucleosynthesis is, but small enough that it runs efficiently, especially if you're doing 3D simulations. And so we have tools that allow us to make approximations to the network and also prune it down, figure out what rates aren't important or what nuclei aren't important, and eliminate those so the network integration will go faster. A simple way to do this is to just sample states that might appear in your simulation. We actually can use YT to read the data directly from a simulation and get this tuple of density, temperature, and a composition from the simulation. But here I just say that set of thermodynamic conditions and slightly higher density, slightly higher temperature. I'm going to put those into a list, and I'm going to say find the rates given this set of states, and I can add as many thermodynamic states as I want, that are smaller than 10 to the minus 30 compared to the fastest rate at any of those conditions. And then I can remove those. I should probably look at what those were. What did it find? It said that these rates are just never important at those conditions. And so then I removed those, and now I have a much simpler network. A lot of those reverse rates went away, and I have fewer rate evaluations. I still have the classic CNO cycle here. I have the hot CNO cycle here as well. I have the proton-proton chain. Even triple alpha survives under those conditions because I put in that higher temperature. But a lot of the reverse rates went away. And that's fine if we stick to those thermodynamic conditions, because those will probably never be important in our simulation. We have other ways to visualize it. You can sort of see as a function of rate and as a function of nuclei what the relative strengths are. You could plot the Jacobian, which is used in integrating the network, and you can see what its sparsity is, and you may or may not want to take advantage of that in your integration. For a reaction network, you want to write out the set of ordinary differential equations that describes how the molar fraction of each of those nuclei evolves in time. And Pynucastro knows how to do that. The networks know how to do that. So I can say, give me the full y dot string, so dy, d molar fraction, d time string for carbon-12. And here's the Python code for that. And it says carbon-12 decreases because of a proton plus a carbon-12 according to the rate proton C12 goes to nitrogen-13, and it increases with proton plus nitrogen-15, creating a helium-4 and carbon-12, and it increases via the triple alpha. And this rate eval is going to be just a simple class that holds all of, we just evaluate the reaction rates once, it holds all those reaction rates that we can then use. And we can output the entire, an entire module that contains the entire set of ordinary differential equations. So all of those dy dt's, all of the Jacobian elements, even allowing for screening if we want to add Coulomb screening to the rates. And this is in Python, but there's analogous ways to do it in C++ that we use directly with our codes. And then I can import that network that I just wrote out, and I can use SciPy's solve IVP, initial value problem, to solve it. Reaction networks tend to be stiff, and so we usually use an implicit solver, and SciPy has this BDF solver that works well for it. And so I can just give it the right-hand side for my module, give it the Jacobian for my module, pass in rho and t as extra data that's needed to evaluate the right-hand side, give it some initial conditions and how accurate I want things, and it'll solve it. It says it was successful. It says that it needed to call the right-hand side function 1,200 times. It needed to call the Jacobian 29 times. It needed to do an LU decomposition 166 times. Different methods will have different workloads on this. So being able to monitor this can also help you understand the performance of your network. And then I can plot it. And I can see here, this is for the conditions in the sun. After about 10 billion years, the hydrogen goes down, helium goes up, and the next dominant nucleus is nitrogen 14, that's sort of the waiting point in the CNO cycle. And so you wind up with nitrogen 14 being built up. We have other rates that we can work with. We can work with tabulated rates that a bunch of different people work out as a function of electron density and temperature, the tabulated rate, the weak interaction rates. And so we have sources from a lot of different places, and we keep adding some. And so electron capture on nickel 56 to make cobalt. This is important in supernova. We can look at it, and this is what the rate table looks like. And we can evaluate it as well, and so we can get the weak interaction rate. This is just in reactions per second. We can also, I know I'm running low on time, we can also explore nuclear statistical equilibrium. I can make a network here that has a lot of iron group nuclei, and I could say for density of 1 billion, a temperature of 6 billion, and an electron fraction of 0.5, solve for NSE, and it does it. And this is the NSE state, since the electron fraction was equal numbers of protons and neutrons, nickel 56 dominates. But if I make the electron fraction smaller, more neutron rich, I start to see that iron 56 dominates. You can also export a table of nuclear statistical equilibrium from this that you can use in the simulation code, and we use it, for instance, for modeling massive stars. I have a number of links. I'll just post them on the website as well. I use this for teaching. The library started off as a code that resulted from me assigning homework that students didn't like. And now I use this library to produce examples for stars, which I'm teaching again this semester, to help illustrate some concepts, because you can work through things interactively. So I'll post those links, and I'll stop here.
Great. Thank you, Michael. We are running a little short on time. Is it okay if I let Sam go and then we can do questions at the end? Okay, great.
Please.
Sam, are you ready to present?
Yep.
Great. So next up, we have Sam presenting on Thornado, a discontinuous Galerkin method for general relativistic hydrodynamics. So take it away.
Yeah. Can you guys see these slides? My green bar went away. Okay, cool. Yes. Yep. Hey, everybody. Yeah, I'll talk about Thornado slash AMRX, which was the work I did for my PhD, which was largely to couple Thornado to AMRX. And so I'm just going to talk about both those codes a little bit, and then some of the coupling that had to go on. So I'm giving this presentation, but a lot of people have contributed to this project, and you can find information about papers and stuff that have come out of the code from the website. Okay, so AMRX is a code that will provide MPI parallelism for CPUs and GPUs, and also block structured adaptive mesh refinement. It works by itself, and you can also couple it to other external codes so that those other codes can make use of the tools that AMRX has. And the relevant part for this talk is that it's designed mostly for finite volume based codes. Okay. And then, so contrast that with Thornado, which is uses DG methods for its discretization. And here's lots of stuff about Thornado. I'm not going to talk about any of it except that it is it's coupled to AMRX. And the original target application of Thornado is core collapse supernova. So it's a neutrino radiation hydrodynamics code. But in principle, it could be used for other applications too. Okay, so yeah, one slide on DG methods. So if you imagine you have a whole domain that you want to solve a PDE over, one way you can do it is to break it up into individual cells. And within each cell, you can approximate, for example, the density of the fluid with a polynomial. And so this cartoon shows what that might look like. And if you choose constant, you can have the function be a constant. And so it would just be one value, this magenta line. or you could increase the degree of the polynomial, and you can get a straight line or a parabola. And the idea is that the higher your polynomial degree, the closer you get to match the solution, as long as the solution is smooth within your element. And one relevant part here is this basis function. This L sub I is a basis function. We usually use Lagrange polynomials for interpolating within the element, and that's going to be relevant right now. Okay, so finite volume methods. You can have high order accurate finite volume methods, and AMREX does that very nicely. I'm going to focus on low order methods because it's easier to make cartoons of that and to explain what's going on. And so when you're doing mesh refinement, you want to either take a coarse cell and break it up into finer cells to increase the resolution, or go the other way. And if you have these low order finite volume methods, that's straightforward. And you want to do this in a way that maintains conservation of mass, for example. And with these methods, it's fairly straightforward. If your density is constant in this whole element, and you want to refine that element, then each new element that you have will just have the same density. And then if you integrate that over the whole element, you get the same mass that you started with. And if you go the other way, you have different densities in these 4 blue cells. You just add them all up and divide by 4, and that gives you a value to use in your coarse cell that will have conservation of mass. And the other aspect of this is these algorithms use numerical fluxes. So you have to compute the flux across interfaces. And so with finite volume methods, it's pretty straightforward. So you integral, and what you do is you can just define that integral across the coarse element to be the sum of the integrals across the fine elements. And if you do that numerically, you end up with this thing on the bottom left for the coarse element, and then you just demand that be equal to the thing on the right-hand side. And with finite volume codes, these 2 things are what is returned by the increment computing subroutine that you have. And so it's easy to just kind of store the first one, store the second one, and then subtract the first one and replace it with the second one. With DG methods, it's not as obvious how to maintain conservation. There's a paper by Kevin Shaw from 2015 that shows how to do this, and it's in the references. It's more complicated because it requires a matrix vector multiplication. Excuse me. And it's designed to basically maintain an L2 norm, and by doing that you can minimize an L2 norm, and by doing that you can guarantee conservation to machine precision. And the complicated part comes with the fluxes, the numerical fluxes. So it's kind of a lot of math here, but the idea is that this J represents these black points, so the degrees of freedom on a coarse element. And you compute the flux across that coarse element, which is this one. So it's just the flux, which is a function of y, and these basis functions, which are defined with respect to the coarse element. The J1 and J2 are these coarse element points. And you want to define that to be equal to the integral over the same domain in y, but using the numerical flux from the fine elements. But using the same basis functions that are defined with respect to the coarse elements. And if you do this numerically, you end up with these expressions. And the issue is that the subroutine that computes the increment will return this for the coarse element, but it will not return this for the fine element, because for the fine elements, these basis functions are different. They're defined with respect to the smaller, the finer elements. And so we had to figure out a way to, basically extract this information and then compute this integral outside of everything else, and then substitute those into the tools that AMRX has to do the refluxing. Okay, so yeah, there's just one figure to show that this thing is working. This is a blast wave in 2 dimensions, and it shows that where the density is high, you get more elements, you have more refinement, and if the tools that we had didn't work, then whenever you had these coarse fine interfaces, you would get junk, you'd get noise that would spoil the solution, and so. Yeah, this is just encouraging to show that that's doing what we want it to do. And so, yeah, what we did for this was just wrote custom interpolation routines within AMRX that do these matrix vector multiplications. And then we also rewrote the numerical flux integral in Thornado in a way that we can make use of the tools that AMRX already has. And yep, that's references, and that was all I had. So thank you.
Great. Thank you, Sam. Let's see. So I think that finishes our presentations for the day. We can take a few minutes to answer some of these questions. I know there were a few still lingering from Michael's presentation. And if anyone has any questions for Sam, feel free to throw those in the chat or to use the raise hand function if you'd prefer. So I could see Michael was answering some questions in the chat, and I don't want to repeat any. Let's see. So I'll go just kind of back up to the top here, if that works. Yeah.
Yeah, that works. I think I
okay.
didn't answer
Brandon's question. Okay, great. Yeah. So Brandon asks, yeah.
It probably can output Coco's friendly C++ with minimal tweaks. It outputs C++ that works with AMRX, which uses the same sort of lambda capturing ideas as Coco's. We just use some AMRX data structures. It probably wouldn't be hard to write it in a way that's friendly for Coco's. I mean, if you could show me a bare bones, example of something that you would want for a network in Coco's, we can make that output work. I don't think that would be hard at all. I just don't have a way to test it. There's a question about P process and weak R process. We keep adding rates. Part of the problem is just finding the rate data, because sometimes it's well hidden in journals. Also, a lot of the rate data is not licensed, so it's always a question of are you able to redistribute it? But we do our best. If there are particular reactions or rate data that is interesting, we can add them. We have all ReactLib. We have the Langankin weak rates. We have Oda weak rates, Suzuki weak rates, the Fowler, Fuller, Newman weak rates, Pruitt and Fuller weak rates. Although apparently there's more of those than were published originally, so we only have what was originally published. But if there's other ones, we can add them as long as we can find them.
And I think you kind of answered both these questions in one. Kamal's question as well there. Yeah, I think that was all the questions that were put in the chat have been addressed.
I had one more.
Oh, go ahead, Austin.
Yeah. So for the pruning rates, is there a safe way to do that so that across a range of conditions, so you don't miss any resonances?
So there's two things. I mean, you can add as many conditions as you want there. So if you sample a simulation, you can add like 100 different conditions and then have it prune it. But we also have this algorithm that came out of the chemistry stuff, this directed graph reduction algorithm that isn't well documented in Pynucastro, but it's implemented, and that's a more robust way because you can add what the error is that you want to optimize for, and have it automatically do the reduction. So that's something I have a student trying to clean up now, and we have to write the documentation for that. But that's a much more powerful way. But just the unimportant rates way, you can just give it a list of 100 different thermodynamic conditions that you care about, and then have it look at it, and it'll do that really fast. Hopefully that answered it.
Yeah. Great. Okay, we have one question in the chat for Sam. Kamal asks, how can we use Thornado for supernovae, and what aspects of it can we analyze?
So we can use it. So we can't use it by itself for supernovae because it doesn't do gravity. But if you couple it to a gravity solver, then you can simulate the hydrodynamics of collapse and bounce. And if you add in a reaction rates table, like Mike was talking about, you can do all these things. And then with that data, you can analyze abundances that you get from fusion reactions, the morphology of the ejecta if you have a multidimensional simulation, velocity profiles, explosion energies. I mean, pretty much anything, because if you have the hydrodynamics and you have the reaction rates, I mean, those are most of the things that produce observables and neutrinos also. And so you can analyze anything in principle, you would want. We don't have tracer particles yet, but that's something we could add. And we don't have magnetic fields yet, but that's something that's being added right now. So yeah, I hope that answers your question.
Great, thank you. Yeah, that was all the questions we had in the chat. If anyone has lingering questions, we have about 5 minutes left today. Feel free to raise your hand. Otherwise.
And then just a reminder, we're looking for organizers. We're looking for talk suggestions. The link was posted earlier. We're also looking to have a session on how people are using AI tools to help them write code and debug code and break code, whatever you do. So if that's also something that you like or dislike, sign up as well, or let us know.
Yes, and big shout out to the few people who have already filled out that organizer form since we started this morning, or yeah, started about an hour ago. So.
All right, I'm going to stop recording.
Great, thanks, Alice.